Phase diagrams. So phase diagrams are incredibly useful when we're looking at state changes. And the major factors that affect what state of matter something is in is the pressure, the external pressure, and the temperature of the system. So a phase diagram looks at the three states of matter and looks at them where they are in relation to those two variables, pressure and temperature. So you'll notice in this generic phase diagram that at very low temperatures and normal pressures, your substance is most likely to be a solid. And this makes sense because solids are characterized by having the lowest kinetic energy, and temperature is a measure of the average kinetic energy. As I increase the temperature, I am more likely to go into a liquid phase and then into a gas phase. If I have an extremely low pressure, so around here, I can actually make that change between phases more easily. At extremely low pressures, I can actually go from a solid straight to a gas. So these lines, these solid lines in the phase diagrams are where the state changes are occurring. And those are the melting points if you're going from a solid to a liquid, the boiling point if you're going from a liquid to a gas, and if you're going straight from a solid to a gas, it's the sublimation point. So if I'm going backwards, this would be the opposite of boiling, which is condensation, and melting, if I was going this way, it would be freezing. Sublimation is something that doesn't occur very frequently, but it can go from solid to gas. And an example of this is what happens in the wintertime or in your freezer. So if you've had ice cubes in the freezer for a very long period of time, they actually look like they've shrunk, and they have, and it's not because your freezer has increased in temperature. It's because sublimation has occurred, and what water was in the form of ice became water vapor. You can also see this in the wintertime on cold days when it has never reached melting point. You'll start to see some of the snowbanks start to shrink, and the shrinking is occurring because you have sublimation occurring. At any given substance, you have a particular pressure and temperature at which all three states of matter will exist in what we call equilibrium, meaning their substances won't change. And that's called the triple point. It's a unique point for every substance that's out there. So, in short, a phase diagram can show us what state of matter anything is at a particular pressure or temperature. You can find the melting point, which is the temperature at which you can have the solid change to liquid at any given pressure, and the boiling point. Or we can find the pressure needed to change the state of matter at any given temperature, right? So I can either read this going across. I keep my pressure the same, and I want to see what temperature I have to attain to get to the melting point or the boiling point. Or I could say, all right, if I want to go from a liquid to a gas and keep the temperature the same, I could decrease the pressure in order to get to that change of state. One thing that a phase diagram doesn't show you is the amount of time or energy required to change the state. So this is a generic phase diagram. If I were to look at what that would change depending on different substances, right? So solid, liquid, gas. Remember that whenever we're changing states of matter, we're overcoming intermolecular forces of attraction. So if we're overcoming intermolecular forces of attraction, it makes sense that if you have a substance that has stronger intermolecular forces of attraction, that the phase diagram would reflect that. So think about it. If you have stronger intermolecular forces of attraction, then at any given pressure, the temperature required to melt something would be higher. So this line would be shifted over. Right, so this is stronger IMFs. Think about the liquid to gas. If I have a liquid to gas as well, if I have strong intermolecular forces of attraction, then I would also expect this to shift over, right? Because the boiling point at any given pressure would also shift over. And similarly, I would expect my sublimation. So I would expect my graph to be transformed, shifted to the right, possibly up, or down, probably down more, right? So this should actually be right here, because I would need to lower the pressure in order to get the same change of state. So this is, green is for stronger IMFs, and this is for weaker IMFs. So where it transforms, whether I shift left or shift right, depends on the IMFs. Another thing that you'll sometimes see is the slant, the slope of my lines. So water is a unique substance in which the slope of its line from solid to liquid actually slants backwards. So this is for water. And this has to do with the unique properties of water. Water is incredibly polar, so you have very strong IMFs, but it's a bent shape. So when I have intermolecular forces of attraction between water molecules, if I want to have it in the solid state, my water molecules, because of their bent nature and because they have strong IMFs, in order to have those maximum IMFs form in the solid stage, leave gaps. Right, so there's gaps between the molecules. So as a result, water in its solid state is less dense than water in its liquid state. This does not happen for most particles. Most particles, when you go from a liquid to a solid state, you get tighter packing and you get a greater density. So because of that, if I increase the pressure, keep something at the same temperature, if I increase the pressure and actually force these gaps to get lost, the intermolecular force of attraction starts to increase and allow the particles to slide past one another, enabling us to be able to transform something from a solid to a liquid state. So an example of this would be ice skating. If I have enough pressure on a very sharp blade, I can increase the pressure over that ice, and I can actually melt that ice. Very little. It's not like the person's going to sink all the way through the ice, but you could do that with a wire. And in fact, there are magic tricks in which you have a wire over a block of ice, and there's very heavy weights around it. And what it does is, at that very thin line where the wire is, it melts the ice, and then the ice freezes above it, and you can have a wire embedded in the ice. And it looks like magic, but it's not. It's just chemistry.